This program has been compiled to explain the maintenance and fault procedures that should be carried out on the Cummins L10 engine. The L10 engine is currently fitted in the Olympian, in a vertical format, and as a horizontal unit in the Lynx and Tiger vehicle ranges. Power output varies depending upon specification and ranges from 180 brake horsepower for most city bus operations through in increments to 290 brake horsepower for high-speed coach operation. All engines within the range are turbocharged with intercooling on the high output engines. The Cummins PT fuel system is used throughout all L10 engine applications. In the first part of this program, we will be looking at the maintenance procedures and adjustments, followed by a range of fault conditions with fault procedures. Although the vertical and horizontal engines may look quite different, the main principles of maintenance, testing, fault diagnosis, and adjustments are similar. To confirm this, we shall carry out some of the exercises on the vertical engine and some on the horizontal. Where differences do occur, these will be referenced. However, before proceeding, be aware of the safety procedures when working on the engine or carrying out running tests. Always ensure adequate ventilation. Shock the road wheels and apply the handbrake. Display a suitable warning notice in the cab when working on the engine, and finally, exercise extreme care when working in the areas of the drive belts, rotating shafts, and cooling fans. When draining the oil, always ensure that the engine is at normal working temperature. On vertical engines, there is only one drain plug. However, on the horizontal, there are two. This one drains the inner sump, and this the outer. Most of the existing L10 engines have two oil filters, a full flow, and a bypass. However, this arrangement will be superseded by a dual-purpose unit known as a combination filter. For reference, the oil filter location does vary on the vertical engine. On early units, the filter is mounted here. But on all new and current vehicles, the filter is mounted on the timing case on the front of the engine. On all horizontal engines, the filters are mounted on the engine sump. Providing the filters have been installed correctly, they can normally be removed simply by unscrewing the cartridge unit assembly using a filter clamp. Make sure that the sealing ring is not stuck on the filter head. The main filter can be unscrewed in the same manner. To avoid undue lag in the oil supply to the engine on initial startup after a filter change, always pre-charge the filter with engine oil before refitting. Before screwing the filter into place, lightly oil the sealing ring, as this will assist future removal. Screw the filter in until contact is made with the filter head, and finally tighten the filter a further 3/4 to 1 full turn. To refill the vertical engine with oil, the exercise is straightforward. Just add oil till it reaches the maximum mark. However, with the horizontal engines, add oil until it shows on the dipstick. Start the engine and idle for at least 2 to 3 minutes. Stop the engine and check the oil level within 1 minute and top up if required. Do not be tempted to exceed the maximum mark. Fuel filter maintenance. The fuel filter is located here on the vertical engine and here on the horizontal engine. On the bottom of the filter, there is a facility to drain off any water that may be present in the fuel. To do this, simply unscrew like this, and when clear fuel is visible, retighten the valve. But do not over-tighten, as damage may occur to the nylon threads. When the vehicle is in service, this exercise should be carried out at regular intervals, as water can collect in the system due to condensation, and water contamination can occur at any time, particularly if the vehicle is fueled from an outside source. If it's necessary to replace the filter, it can again be unscrewed. However, be aware, on a horizontal engine, fuel may siphon from the tank if the level is high within the fuel tanks when the filter is released. A seal on a replacement filter should again be lubricated with engine oil prior to fitting. To assist with fuel priming on startup, fill the filter with clean fuel, assemble the fuel filter until contact with the filter head is again made, and then tighten a further 3/4 to 1 full turn. When complete, start the engine and any air remaining in the system will automatically be purged. The cooling system. The cooling systems on Cummins engines rated at the medium to high power ratings are charged with a chemical additive to protect the water system components against corrosion, and a water filter to collect any debris contained in the water. The chemical additive has taken two forms. On earlier engines, DCA, and on current units, DCA4. The DCA4 additive was introduced as it is more compatible with modern anti-freeze mixtures which contain a higher level of anti-corrosive additive. During servicing, it's important to check that the additive level is correct, which should be 1.2 DCA4 units to 1 gallon of water, rising to a maximum of 2 DCA4 units per gallon of water. If the level is either below or higher than specified, damage will result. One of the areas which is particularly at risk is the cylinder liner walls. The cylinder liners on the L10 are in direct contact with the cooling water and are known as wet liners. During normal running, due to vibrations from the liner walls, unless water additive is in the cooling system, the liners will erode badly and in severe cases will allow water into the engine. Here is an example of this problem. As an alternative, if the mixture is over-concentrated, the water will attack any aluminium components and solder which is present in radiators and heat exchangers. The DCA4 additive can be introduced into the engine in two different ways. A range of filters pre-charged at different levels, or alternatively liquid DCA4. Under normal circumstances, for routine servicing, you would only fit a service filter of a low value just to maintain the DCA4 level. The higher value filters would only be used if the water system had been completely drained. As an alternative, after drain down, you could use a low value filter and top up with liquid DCA4. For example, if the system has to be recharged, first establish the water system capacity. If, for example, the system holds 10 gallons, you would require 12 DCA4 units. First, select a filter close to the value required. In this example, we're using an 8 DCA4 filter and topping up with 4 units of liquid. To carry out routine maintenance, first turn off the 2 isolation taps and then unscrew the filter. select a low-value service filter, in this instance 4 units. Prior to fitting, lubricate the seal. Again, do not over-tighten. Remember to turn the taps on. If you wish to check the DCA4 level after fitting a high-value filter, the engine should be brought up to normal working temperature and run for approximately half an hour to allow the additive from the filter to disperse into the cooling system. If you're required to check the DCA4 level in a cooling system, a special test kit is available. The kit consists of a plastic cup, syringe, plastic measuring container, test strip bottle, and a special test solution. To conduct the test, first fill the plastic cup half full with a sample of coolant. With the syringe, draw the coolant sample in until this mark is reached. And then dispense into this measuring container. Next, fill the container up to this mark with the special test solution. Swirl the mixture to ensure complete mixing. It should be noted that some coolants may become cloudy at this point. To continue, remove a test strip from the bottle and dip it into the mixture. Shake off any excess liquid. A period of at least 4 minutes should be allowed for the colour strip to develop. However, do not allow the developing time to exceed 5 minutes. From this block colour chart in the test kit, compare the test strip colour. The chart gives the recommended action that should be taken depending on the colour of the strip. As mentioned earlier in the programme, engines with a power rating of 215 brake horsepower or below do not require a DCA4 additive. However, it's important to note that the antifreeze mixture should be at 50% concentration to offset any corrosion of the water system. It should also be noted that if dilution of the antifreeze solution takes place and drops to a concentration of 10 to 15%, the mixture is more corrosive than ordinary water. As an alternative, if the antifreeze strength is above 60%, sludging of the cooling system will occur. Providing the antifreeze is ethylene-based, a hydrometer can be used to assess the mixture strength. However, if the antifreeze is a propylene mixture, a refractometer has to be used. It's important to note that ethylene and propylene antifreeze should not be mixed in the cooling system. Engine breathing. On the vertical engine, the engine breather is located here. It does not require any form of service. However, on the horizontal engine, there is a filter located here, which should be inspected and cleaned at oil change periods. Alternator drive belt and adjustment. On the L10 engine range, Poly V drive belts on the alternator are used. The belt adjustment on the vertical engines is on the alternator cradle. However, remember to slacken these two mounting bolts prior to adjustment. On the horizontal engine, adjustment is carried out by movement of this idler. On this application, slacken the idler lock nut and turn this screw clockwise to increase tension. To avoid unnecessary belt wear due to belt slip, or alternatively high-bearing loads on the alternator, the belt tension should be checked with this special gauge. Positioned here on the vertical, and here on the horizontal. Some early L10 engines were fitted with a 10-groove belt and later models with a 12-groove. For reference, the belt tension should be set at 20 pounds per groove. In this example, we have a 10-groove and should be set at 200 pounds on the gauge. If a new belt is installed, be aware that it stretches rapidly on initial running. Therefore, run the engine for 10 to 15 minutes and recheck the adjustment. PT fuel system. To assist with the fault diagnosis later in the program, let's now look at the fuel system on the L10 engine. The Cummins PT fuel system differs considerably from a conventional fuel injection system. The fuel pump is a low-pressure unit which delivers fuel via a single pipe and drillings in the cylinder head at pressures ranging from 80 to 200 pounds per square inch, depending on specification. The individual injectors within the cylinder head are mechanically operated by the engine camshaft via a pushrod and rocker lever. During normal operation, the high pressure for injection is generated within the injector at pressures in the order of 20,000 pounds per square inch, which is approximately twice the pressure of a conventional system. To continue, let's look in more detail at the fuel system and the principles of operation. When the engine is in operation, fuel is drawn from the main fuel tank through a filter and into a gear-type pump. Fuel under pressure first flows to a damper unit, which smooths out any pump pulsations, and then on to a magnetic screen filter, which collects any small metal particles which may come from the gear pump. The fuel then continues to the governor plunger. Providing the engine is in the idle position, fuel continues to the throttle shaft control, which is closed. However, fuel can take an alternative path around the throttle sleeve and onto the air fuel control, known as AFC. At this stage, the AFC is closed. Fuel can flow through this drilling and past this screw, known as the no-air screw. The fuel supply continues through to the injector via the fuel cut-off valve. On the inlet to the injector, there is a screen filter and a metering hole. Providing the injector is not injecting, the plunger is held down into the cup. During this condition, all the fuel from the main fuel pump is able to pass freely through the injector and back to the tank. Just prior to the point of injection, the plunger moves up, which first of all cuts off the return and allows fuel to fill the chamber below the plunger. As the plunger moves down, this section of the plunger cuts off the fuel supply and the fuel is pressurized and atomized fuel passes into the cylinder. You will note that the plunger in this position allows the fuel return to the tank to open up once again. Two of the main factors controlling the amount of fuel entering the engine are the length of time the plunger is in the up position and also the fuel pressure entering the injector. And this is where the system derives its name, the PT system. Pressure, time. If the engine is at idle, the pressure supply to the injectors is controlled by this spring and button. The spring tension, which is adjustable, dictates the pressure to the injectors. For example, if the engine revs tend to increase, the pressure output from the transfer pump increases, which lifts the button off the end of the governor plunger, allowing the excess fuel pressure to return to the suction side of the transfer pump. Thus limiting the fuel pressure to maintain the correct idling speed. It should be noted that the idle speed can be increased or decreased by adjusting the spring tension. When the throttle is open fully, the throttle shaft port opens. The governor plunger moves to the right, initially closing the idling pressure relief and thus overriding the idling spring. Because the return is cut off, and also the idling fuel sleeve, all the pump output is available, which results in a pressure rise through to the injector. With the increased pressure, the injector supplies more fuel to the engine, resulting in an increase in power and revs. Initially, the AFC control is closed to limit the amount of fuel going to the injector. However, as the turbocharger starts to work, the air pressure within the inlet manifold, known as boost pressure, increases. This pressure increase is also felt on the AFC piston, which moves to the left, progressively opening up this port, which allows more fuel to the injector, and a consequent further increase in engine power is available. Without the AFC giving this initial fuel control on engine pickup, the engine would produce black smoke until the turbo boost pressure came up. The maximum fuel pressure is controlled by this spring. And again, as with the idling pressure, the piston will move away from the governor plunger and control the maximum pressure by diverting surplus fuel back to the suction side of the pump. As the engine reaches the design maximum speed, the governor weights move this plunger further to the right until the main fuel supply to the throttle shaft is closed. This reduces the engine fueling to control the maximum revs. To complete in this area, let's consider a high-speed overrun condition with the throttle closed. The governor plunger would be in this position, which is a high-speed condition, and would be covering the idling and throttle leakage supply ports, and also the throttle shaft supply would be closed, shutting the fuel supply off to the engine. In practice, however, there is always a controlled amount of fuel allowed through to the injectors, even in this condition, via the throttle shaft. This is known as throttle leakage. Without this facility, the engine would be slow to respond to throttle operation, particularly after a hill descent, because there would be a delay while the pump recharges the fuel rail to the injectors. To complete the fuel system theory, there is a drain pipe connected to the AFC which takes account of internal leakage and fuel displacement during the operation of the AFC. And finally, a pump cooling line is connected from the pump to the return. For guidance, let's look at the location of some of these items on the fuel system. The screen filter is here, retained by this plug and spring. Under normal conditions, the filter only requires attention at fuel pump overhaul periods. This screw controls the throttle leakage setting, and unless authorized, no attempt should be made to carry out any adjustment. For guidance, however, for diagnostic purposes, if the screw is too far in, the engine will not die down, and if it's too far out, this will reduce the throttle leakage fuel flow to the injectors, causing slow throttle response. The no-air screw and maximum throttle stop are housed under this cover plate and are only available to fuel pump specialists. Providing you have the necessary special equipment and authorization, the engine idling speed can be adjusted as required by first removing this plug. If the special tool is now inserted into the fuel pump housing, clockwise movement will increase the idling speed and anti-clockwise will reduce it. The idling speed should be set to 600 RPM. The AFC control is here, and also the shutdown valve. It should be noted that if the shutdown valve fails electrically, it fails closed. Under these conditions, if you wish to start the engine, screw in this override screw fully like this to start the engine. During this section, we will be looking at the adjustment procedures for valves and injectors, in this example on a horizontal engine. However, the procedure is identical as that on a vertical. On the L10 engine, there are 2 inlet and 2 exhaust valves per cylinder. These are actuated by rocker arms via crossheads. The long rocker arm is the exhaust and the short the inlet. The center rocker is for the injector. If you're required to remove the injector, first release the lock nut on the injector rocker arm and adjust the screw, and remove the main injector push rod. Then the injector link. Next, release the exhaust rocker push rod. With both arms free to rotate, you can now gain access to the injector clamp for removal. To remove the injector, a special extractor is available which locates on the injector like this. During the removal of the injector, take care not to drop the plunger or mix it with any other injector plunger, as each plunger is matched to each individual injector. Before refitting the injectors to the engine, replace these 3 O-rings. Failure of these seals would create the following problems. The upper seal will allow fuel from the return to leak into the engine and contaminate the engine oil. The middle seal will allow fuel to short-circuit from the injector supply through to the return, resulting in a drop in fuel pressure, with a consequent power loss plus a possible pressurization of the return line, giving a slow die-down and run-on. The lower seal will allow fuel rail pressure to seep into the combustion chamber, causing black smoke and a drop in fuel pressure with a resulting power loss. More details on this subject will be given in the fault diagnosis section of this program. If replacement injectors are to be fitted, always check the part number, located here, is suitable for the engine, because there are many variations in spray pattern, spray holes, and fuel supply orifices to suit the various engine types and ratings. Make sure that the injector hole is clean before replacing the injector. Lubricate the seals and push the injector into place. It should, if located properly, snap into position like this. Replace the clamp and tighten the nuts evenly to a torque of 132 pounds-inches. Failure to comply with this requirement may cause damage to the injector or jam the injector plunger, causing a misfire. Therefore, when the injector is in position, check that the plunger is free to move. If in order, replace the pushrod and link. To complete the injector replacement, the injector stroke must be set. To do this, we must set the engine in the correct position for each injector. Timing marks to do this are on the crankshaft pulley on the horizontal engine and on the auxiliary pulley on the vertical. In each instance, you have A, B, and C marks. Because the engine is a four-stroke, we must use the A, B, and C marks twice if we wish to set all the injectors. A table outlining the engine positioning for injector setting is contained within the support notes. For example, if the C mark is aligned, we must establish which stroke the engine is on. If the valves on number 6 cylinder are closed, we can set the injector on number 2 cylinder. Or alternatively, if the valves on number 1 are closed, we can set number 5 injector. In this particular example, the valves are closed on number 6. Therefore, we can set the injector on number 2 cylinder. First, slacken the lock nut and tighten this screw, using this special torque wrench, which is set to break at 6 pound-inches. Next, retighten the lock nut. To ensure that the adjuster screw does not turn, upsetting the initial setting inside the screw when the lock nut is tightened, a special tool is available which holds the central screw while the lock nut is tightened. This tool also provides a facility to use a torque wrench to ensure the correct torque is applied to the lock nut. When the injectors are adjusted correctly, during the injector stroke, the plunger just contacts the injector cup at the end of injection, and to ensure that all the fuel is expelled from the injector, the camshaft is designed to load the injector plunger for a short period to squeeze out any fuel that may be remaining. This is known as cam nose crush. This feature avoids any possibility of fuel being left in the injector, which would result in a carbon buildup in the cup. You should be aware that if the injectors are not set correctly, they will affect the fueling of the engine. If the pushrod is slack, this will cause black smoke, because the injector, when collecting fuel prior to injection, will be in the fueling position longer than normal and collect more fuel. This condition is known as set long, and in addition, the cam nose crush will not be effective, and the injector will carbon up over a period, resulting in a misfire and possible damage to the cup. As an alternative, if the pushrod is set tight, it will reduce the filling period of the injector, causing an underfuel condition and reduced engine power. This condition is known as set short. In extreme cases, damage to the injector cup and camshaft may result because the crush imposed on the injector will be in excess of the designed limit. Therefore, care must be taken during the setting procedures. The next area to discuss is the valve clearance and crosshead adjustment. The A, B and C marks are again used to position the engine for the individual cylinders, and again a table for guidance is contained within the notes. In this example, we're on the C mark, and we can therefore set the rockers on number 6 cylinder. First, release the inlet and exhaust rockers, and remove the push rods. Next, release the crosshead lock nuts and the adjuster screw. Push the crosshead down like this and screw in the adjuster screw until contact is made with the valve head. And again, tighten the lock nut, taking care not to move the screw. Always position the adjuster away from the rockers on the crosshead. Otherwise, a foul condition will occur on the rocker arm. The main rockers should be set to 14 thou on the inlet and 27 on the exhaust. Again, the same torque spanner will ensure accurate setting and torque of the adjuster lock nut. Let's now move into the area of fault diagnosis. In this section, we will be carrying out the fault diagnosis routines on the vertical engine in an Olympian. The diagnosis procedures for the horizontal engine will be identical. During these tests, we will be using special test equipment consisting in the main of a pressure and vacuum gauge and a fuel sight glass. Let's move now to our first engine fault category. Engine will not start. On the assumption that the engine is cranking at the correct speed and fuel is available in the fuel tank, the first check is to establish whether the fuel is reaching the injectors from the fuel pump. To do this, slacken the fuel supply pipe close to the cylinder head. And crank the engine. If there is no fuel, you should next manually override the shutdown valve, as it may have failed electrically. An override screw located here should be screwed in fully. If the engine now starts, the shutdown valve and its electrical circuit should be checked. Should there still be no fuel available after operating the override screw, remove the filter element and check whether it has fuel. If it has, check the fuel pipe between the filter and the fuel pump. If no fault is found, the fuel pump should be removed for inspection. As an alternative, if there had been little or no fuel available in the filter, a careful check must be made on all the fuel suction pipes and connections from the filter back to the tank for air leaks and damage. On the assumption a fault is identified in the suction pipe, it will be necessary to prime the filter before attempting to start the engine. On certain occasions, it may also be necessary to prime the fuel pump by introducing fuel into the suction pipe while cranking the engine. At the beginning of the fault routine, if fuel had been available to the injectors, the most likely reasons for a no start in this situation is that the engine is not receiving sufficient fuel, particularly if the engine is cold or a high level of air is present in the fuel. During throttle operation, check the lever movement on the fuel pump and ensure it moves from the idle position to the maximum screw. On city bus applications, the fuel lever is spring-loaded and should knuckle like this if correct, confirming that the maximum stop is in contact. On coach applications, a road speed governor is fitted and the maximum stop cannot be seen. However, if set correctly, the back plate of this unit should deflect slightly when full throttle is reached. If this movement is not available, check the air actuator system before adjusting the throttle linkage. If adjustment is carried out on the linkage, make sure, if the vehicle has a ZF automatic gearbox, that this unit, known as a load sender, is also adjusted so that it aligns with this mark at idle and this at full throttle. Providing all is in order, a check should be made for air in the fuel. To do this, install a sight glass between the pump and filter. Once again, crank the engine. If fuel aeration is not visible in the sight glass and there is little or no fuel movement, you should proceed to cover this drain hole up on the pump drive housing. And if the engine starts after a further period of cranking, this indicates a faulty oil seal in the pump drive housing, which is allowing air to be drawn into the fuel system. It should be noted, however, that on all current L10 engines, this hole has been deleted. Another potential point where air can enter the fuel in the pump is via the fuel pump cooling line. A non-return valve is located here in this elbow. And if it fails to seat correctly, the pump will pull air from the return line. Access to the valve for inspection can be gained by removing this elbow. If we refer back to the original test with the sight glass and air had been evident, you should replace the filter and seal and carefully check all the pipe connections from the filter back to the tank. Slow, die down and run on. From the fuel system diagram, you will recall that the engine speed is related to the fuel pressure to the injectors. Therefore, if the rate of fuel pressure drop is slow, the engine will be slow to die down, and also slow on shutdown. With this problem, first check that the throttle mechanism is responding correctly and the fuel pump lever is returning fully onto the throttle leakage stop. Providing these are in order, you should check for air in the fuel system. If air is present, because of the expansion characteristics, it prolongs the pressure die-down when the throttle is closed or when the shutdown valve is operated. In addition to these problems, the air will also cause the engine to be slow on acceleration, and it may cause the engine to surge when at idle. If no air is evident, we should now check for pressurization of the fuel return line, as this can be caused by a damaged pipe or a faulty tank vent. In this instance, your first check will be to release the fuel filler cap. Take special note that if the tank is pressurized, fuel can be thrown out of the filler neck. Therefore, take precautions to contain this spillage. If the engine now responds correctly, the tank vent is at fault. Within the fuel tank vents, there is a check valve, which is normally in the up position. The purpose of the valve is to eliminate any fuel spillage should the vehicle turn over in an accident. It is important that the valves are fitted the correct way up, and the connecting pipe to the fuel tank rises continuously, with no dips. This also includes the connecting elbow, which again must point upwards. Take note, if there is a dip in the fuel pipe and fuel lodges in this will give slight pressurization on the fuel tank. Within the filler neck of the fuel tank, provision has been made to avoid overfilling. With the Cummins engine, it's necessary to leave 5% by volume airspace in the tank to take account of fuel expansion due to heat. Failure to leave this gap will result in slow engine die-down until fuel space has been generated by normal fuel consumption. When filling the tank, do not attempt to trickle fill the tank once the fuel nozzle has shut down. Otherwise, you will override this fuel level facility in the fuel neck and overfill the tank. If we refer back to the original problem and the fuel tank had not been pressurized, you should disconnect the fuel return pipe close to the engine and run the return pipe direct into a container. Start the engine and check the rate of die-down. If correct, continue to disconnect the pipework in stages back to the tank until the faulty pipe section is identified. On horizontal applications, because the fuel level in the tank can be higher than the engine, a non-return valve is fitted in the return line to stop the fuel siphoning into the engine after shutdown. When working correctly, it requires a pressure of 0.3 pounds per square inch to lift the valve. As part of the checks, make sure that the valve is free and not restricting the return. Although not part of this fault routine, it should be noted in this area that if the valve fails to seat after engine shutdown, the fuel from the tanks, if high enough, will flood one cylinder via the return line, because one injector will be in the fuel cycle. It will cause, in extreme cases, a hydraulic lock when attempting to start the engine. On the assumption that all is in order in these areas, the next suspect area is a fault in the check valve in one of the injectors. It should be noted that a faulty check valve extends the engine shutdown period to approximately 30 seconds. The function of the check valve when working correctly comes into operation as the injector starts to move down on injection. There is a short period when the supply port is still uncovered and the fuel is pushed back under pressure towards the supply port. The check valve drops onto its seat as this pressure builds up, isolating the feedback to the supply rail. If the valve fails, fuel under pressure is fed to the remaining injectors and allows the engine to run until all the fuel is consumed within the faulty injector. If you wish to locate the faulty injector and no special equipment is available, you should proceed to substitute each injector in turn with a replacement injector. If the engine shutdown is checked at each stage, when the faulty injector is reached, the engine will shut down normally. Unless the necessary facilities and equipment are available, no attempt should be made to strip the faulty injector. Remember also to inspect or replace, if necessary, the injector O-rings, as specified earlier in this program, as these can contribute towards this problem. As an alternative, providing the necessary tools are available, it is possible to isolate each injector in turn by holding down the rocker arm. When the faulty injector is held, the engine will shut down normally when the stop control is operated. This hold-down tool could also be used if you wish to identify an engine misfire. You will notice in this example we have used a horizontal engine. However, be aware that the turbocharger oil drain pipe has been temporarily extended to carry the return oil back to the engine during this running test. If the problem still persists, there is either an error in the setting of the throttle leakage screw or a fault within the fuel pump. Low power, no smoke. On the assumption that there is no problem with the vehicle brakes and retarder systems, if this condition exists, it is due to insufficient fuel being delivered to the engine. Our first check, therefore, in this instance, would be to ensure that full throttle is available at the fuel pump as previously explained. If in order, proceed to check for air in the fuel system. And again, if correct, a vacuum gauge should now be connected into the fuel suction pipe. With the engine running, if the reading is in excess of 5 inches of mercury, the filter must be changed. If this fails to correct the problem, carefully check the pipework back to the tank for restriction. If these areas are in order, you should now proceed to check the AFC piston. To do this, disconnect the AFC pipe and also the AFC drain pipe. Next, connect this test pump and gauge onto this connection. Pump up the pressure to 25 pounds per square inch. The pressure should remain if the piston is correct. You should also note that when the AFC is pumped up, fuel should be expelled from the AFC drain, confirming movement of the piston. Therefore, if you're unable to maintain the pressure, this indicates a piston problem in the AFC. And if fuel is not displaced, this indicates that the AFC mechanism is jammed. Providing there are no problems, our next check is to carry out a fuel pressure reading between the pump and injectors. This is known as a snap pressure reading. The test point is here, on the shutdown valve. Insert the test adapter and gauge. With the AFC still fully pressurized, next start the engine and run for 2 to 3 minutes to allow any air in the system to be dispersed. If the throttle is now snapped open fully, the fuel pressure will be recorded on the gauge. Be aware that the maximum fuel pressure is only available for a short period when the engine is accelerating and will drop at maximum revs as the governor cuts in. The maximum fuel pressure reading will vary depending on the engine power rating. In this example, the engine is rated at 180 brake horsepower, and the reading should be in the region of 80 to 95 pounds per square inch if it's correct. Pressure readings for the remaining engines in the range are contained within the support notes. If the fuel pressure readings are substantially below these figures, there is a problem with the fuel pump. However, before removing for testing, be aware that failure of an injector center O-ring can cause a drop in pressure, as mentioned earlier in this program. It should be noted that if the power loss is only on initial engine pickup, this would point to an incorrect adjustment of the no-air screw. No attempt should be made to alter the setting on this screw unless you're authorized to do so. If the pressure had been in order, the injector adjustment must be checked. You will recall that if the injector is set short, an under-fuel condition will occur. In this condition, you should assess whether the engine is down on power or normal. The engine will black smoke with the correct fuel and insufficient air, or alternatively, black smoke with the correct air supply and an over-fuel condition. In the first category, the engine will be down on power, and in the second instance, the performance will be normal. Therefore, to avoid unnecessary checks, always identify the category. Let's first of all look at black smoke with normal power. First, check the fuel pressure. If this is substantially higher than specified in the support notes, the fuel pump needs to be removed for inspection. If in order, check the return pipe for restriction and also the tank vents. However, if there is a fault in this area, the black smoke would be accompanied by slow die-down and run-on, as discussed in earlier fault conditions. If there is no problem in this area, next check the injector adjustment. You will recall that if these are set long, the injector will inject more fuel. Remember also to check the injector specification. If it is found that the black smoke is only evident on an initial engine pickup, and you've confirmed operation of the AFC, this is an indication that the no air screw is incorrectly set, allowing too much fuel through on initial engine acceleration. Let's now consider a black smoke condition with low power. The first item to be checked in this instance is the air cleaner for restriction. Located in the air intake trunking is a depression indicator which monitors the condition of the air cleaner. This unit indicates red when the depression in the intake reaches 20 to 25 inches of water. The unit can be reset after rectification by pressing this button. Whilst in the area of the air cleaner, it's always advisable to carefully check the air intake trunking for holes or damage. Remember that the smallest of holes will allow unfiltered air into the engine, resulting in serious damage to the turbocharger and cause a high wear rate on pistons, rings and liners. In extreme cases, the engine will fail at mileages as low as 10,000. If all is in order with the air cleaner, next check the exhaust system. If the exhaust is restricted in any way, this affects the exhaust gas scavenging in the cylinder, with the result that less air is drawn into the engine. There are three areas which can give restriction problems in the exhaust: the silencer, tailpipe, and the turbocharger, which may be seized or running too slowly. Or finally, if fitted, an exhaust brake unit may be jammed in the closed position. On the assumption that there is no obvious damage to the exhaust pipe or silencer, you should proceed to check the turbocharger. On the Olympian, it is mounted at the back of the engine, and here on the horizontal engine. To carry out this work, remove the intake and exhaust trunking. Carefully inspect the condition of all blades on both the compressor and turbine wheels. If, for example, the air cleaner or trunking has allowed dirt through, the compressor wheel will be heavily pitted. It should be noted that the compressor shaft will rock on its bearings, and this should not be interpreted as a fault. In general terms, providing the shaft rotates freely without the turbine or compressor wheels fouling the casing, when loaded diagonally, this is a reasonable indication that the turbocharger is serviceable. Should any doubt exist, check the end float on the turbocharger shaft using a dial gauge. The clearance, if correct, should not exceed 3 thou. To establish the running clearance between the casing on the compressor and turbine wheels, lightly load the shaft diagonally and check the clearance on the opposite blade. The compressor blade clearance should be 8 to 18 thou. And on the turbine wheel, 11 to 19 thou. Moving now to the exhaust brake, if fitted. If the exhaust brake has jammed in the closed position, the engine will not only smoke badly, but it will also be unable to achieve engine speed much above idling. If this fault characteristic is evident, the exhaust brake unit should be removed and serviced. Program summary. To assist with the fault diagnosis section of this program, we suggest that you have to hand the fault diagnosis booklet for reference purposes. Should there be any doubt as to any of the procedures contained in this program, you should seek further advice or refer to the Vehicle Maintenance and Workshop Manual. Always use the recommended engine oil and filters to ensure correct engine lubrication and levels of oil, fuel and air filtration. Remember also the importance of maintaining the cooling system to the correct levels of DCA4 or antifreeze as applicable. With the fault diagnosis, always identify the fault category accurately and follow a logical pattern to identify the fault, and finally remember the safety precautions when carrying out any work on the engine. We trust the information contained in this program will be of assistance when carrying out maintenance and fault diagnosis on the engine.